Good evening, scholars. Tonight's lesson really is a continuation of our previous lesson on balancing chemical equations. In this lesson, I'm going to balance three chemical equations. And in balancing these three chemical equations, I hope to illustrate to you three shortcuts, hints, or suggestions that might be able to help you tackle more complex chemical equations. Here are the three chemical equations that will balance in this lesson. In our first example, we are to balance the chemical equation for the reaction of iodine with sulfur dioxide and water to produce hydroiodic acid and sulfuric acid. You recall from our previous lesson, the first thing we want to do is make an inventory of all the different types of atoms in this reaction. We do so by making a list, and we start by listing all the different elements that we see in the chemical equation. I see iodine, sulfur, oxygen, and hydrogen. Next, what I want to do is make a list of how many atoms are on the reactant side and compare that with the product side. So looking at the equation and starting with iodine, looking at the reactant side, the side that the arrow points away from, I see that I have 2 iodine atoms, 1 sulfur atom, 3 oxygen atoms, and 2 hydrogen atoms. Going to the product side, the side that the reaction arrow points to, I notice that I have 1 iodine, 1 sulfur atom, 4 oxygen atoms, and 3 hydrogen atoms. In our next step, we're going to put a box around each reactant and product. And after we write our boxes, the next thing we want to do is begin to balance the atoms. This is where my first hint or tip of the night comes into play. When you're balancing a chemical equation, keep an eye on elements that are found in more than one reactant or product. If you look at oxygen in this reaction, you'll notice that it is found in one product, however, it's found in 2 reactants. This imbalance potentially causes us some issues in trying to balance oxygen outright. And so my first suggestion of the night is that if you have a situation like this where you have an element that's found in more than one reactant or more than one product, save that element to balance last as you're balancing the atoms. And let me show you what I mean. Starting with iodine, I notice that I have 2 iodines on the reactant side, 1 on the product side. So I need to get 1 more iodine atom on the product side. I look at the boxes on the product side, and there's only one box that contains iodine atoms, and that's a hydroiodic acid box. So I'm going to add 1 more HI molecule to this side. Now I have 2 iodine atoms on the product side. But I'll notice that in this box of hydroiodic acid, it not only contained iodine atoms, it also contained hydrogen atoms. So I need to readjust my list to account for this additional hydrogen that was added. So on the product side, I now have a total of 4 hydrogen atoms. Next on my list is sulfur. I can see that currently it is balanced 1 to 1. And now I'm going to skip over oxygen for reasons that I mentioned earlier. And I'm going to move on and I'm going to balance the hydrogen. I have 4 hydrogens on the product side, 2 on the reactant side. I need to get 2 more hydrogen atoms on the reactant side so that the hydrogen's balanced in this equation. So I find the box that contains hydrogen atoms. That would be a water box. And if I add 1 more water molecule to the reactant side, now count up the hydrogens and find out that I have 4 hydrogens on the reactant side. So now my hydrogens are balanced. But I'll notice that that box of water not only contained hydrogen atoms, it also contained oxygen atoms. So I need to readjust my list to account for this extra oxygen that was added. So if I count up the total number of oxygen atoms on the reactant side, I now have 4. And it just so happens that that now balances with the product side. And as I scan over my list, all elements are balanced from one side to the other. And so all I need to do now is count up the boxes to get my coefficients. 1 box of iodine molecule, 1 box of sulfur dioxide, 2 boxes of water, 2 boxes of hydroiodic acid, and 1 box of sulfuric acid. As I finish up my work here and write out the balanced chemical equation, I'm going to leave off the boxes and coefficients of 1. And so my final answer is I2 plus SO2 plus H2O yields HI and H2SO4. In our second example, we are to balance a chemical equation of the reaction of ethane gas with oxygen gas to yield carbon dioxide and water, a classic combustion reaction. Just like always, we're going to make a list of the different types of atoms in this reaction. As I scan across the equation, I see that there are carbon atoms, hydrogen atoms, and oxygen atoms. I'm going to make a count of the carbon, hydrogen, and oxygen atoms on the reactant and on the product side. Starting with the reactant side, I see that there are 2 carbon atoms, 6 hydrogen atoms, and 2 oxygen atoms. Looking at the product side, I find 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms. Next, I want to put a box around each reactant and product. Having balanced this chemical equation beforehand, I know that this is a pretty tricky equation to balance due to just simply the number of hydrogen atoms in this equation. Which leads me to my second shortcut, hint, tip, suggestion of the night. And that is, if you get into a situation where you are just scratching your head trying to get the atoms in a chemical equation to balance and you're not having good success, then stop what you're doing, take a deep breath, and remember this little tip. When in doubt, whip a 2 out. And what do I mean? The 2 comes from the fact that you can maybe help yourself out by putting a coefficient of 2 at the beginning of your chemical equation. And what this means is we are going to double up the amount of ethane that we have in this equation. So I'm going to go ahead and put a second box here, C2H6. What I'm going to do is I'm going to recalculate my inventory list to account for this change. And so as I go through and do that, I see that I have 4 carbons on the reactant side and a total of 12 hydrogens on the reactant side. And so having done that, I want to go ahead now and try to balance the chemical equation. So starting with the carbon, I have 4 carbons on the reactant side. I need to get 3 more on the product side to have a total of 4. So scanning the product side for a box that contains carbon atoms, I find the carbon dioxide box. And if I add 3 more boxes of carbon dioxide, I now have a total of 4 carbon atoms on the product side. But in this box of carbon dioxide, it not only contained carbon atoms, it also contained oxygen atoms. So I need to make an adjustment to my inventory list to account for this extra oxygen that was added. So now I have a total of 9 oxygen atoms on the product side. All right, next on my list to balance is hydrogen. I have 12 hydrogens on the reactant side and 2 on the product side. I need to get 10 more hydrogens on the product side. I notice that the box on the product side that contains hydrogen is a water box, and it contains 2 hydrogen atoms per water. So if I add 5 more waters, I will have a total of 12 hydrogen atoms on the product side. Now these boxes of water also contained oxygen atoms. So I need to readjust my list to account for the extra oxygen that was added. Adding up the oxygen atoms, I have now a total of 14 oxygen atoms on the product side. Now having saved oxygen for last, for obvious reasons, I need to get 12 more oxygens on the reactant side so they're balanced with the product side. So if I add 6 more boxes of O2 molecule, I now have a total of 14 oxygen atoms on the reactant side. Looking at my inventory list, each type of atom is balanced from the reactant to the product side. So now what I want to do is just simply count up my boxes to get my coefficients. I already have 2 for the ethane molecules. I have 7 boxes of O2, 4 boxes of CO2, and 6 boxes of H2O. To finish up and write my balanced chemical equation, I'm going to leave off the boxes and any coefficient of 1. So my balanced chemical equation becomes 2 ethane molecules reacts with 7 oxygen molecules to yield 4 carbon dioxide molecules and 6 water molecules. In my final example tonight, I'm going to balance a chemical equation for the reaction of potassium hydroxide with cobalt-2 phosphate to yield potassium phosphate and cobalt-2 hydroxide. Before I start putting down a list of different atoms, I want to bring the students' attention to something very unique about this type of reaction. First thing you will notice is that there are polyatomic ions that are in this chemical reaction, hydroxide and phosphate. Another thing that the student will notice is that these polyatomic ions stay intact from the reactant to the product side. And what I mean is hydroxide is not getting broken up into individual oxygen and hydrogen atoms. And the phosphate ion is not getting broken up into individual pieces. Each of these polyatomic ions are maintained throughout the course of the reaction. The only thing that's different is what they're bonded with. And so this leads me to my third hint, tip, suggestion, shortcut of the night. And that is when you are balancing a chemical equation that contains a polyatomic ion, if the polyatomic ion is maintained throughout the course of the reaction, in other words, it's not broken up, then instead of balancing individual atoms, balance polyatomic ions. And so you're probably scratching your head and you're being like, what the heck is he talking about? So let me go through and balance this chemical equation and show you what I mean. So as I'm filling out my inventory list, I notice that I have potassium and hydroxide and cobalt and phosphate ion. Now the reason why I'm writing out the individual polyatomic ions, once again, is because these ions are not broken up during the course of the chemical equation. If they are, you have to break them down into their individual elements. But because they're not, I'm going to keep these together and balance polyatomic ions. So looking at the reactant and product side, first starting with the reactant side, I notice I have 1 potassium, 1 hydroxide ion, 3 cobalt atoms, and 2 phosphate ions. On the product side, I have 3 potassium atoms, 2 hydroxide ions, 1 cobalt atom, and 1 phosphate ion. Next, I'm going to put a box around each reactant and product. And now beginning with potassium, I notice that I have 3 potassiums on the product side, only 2 on the reactant side. So I need to get 2 more potassiums on the left side of the arrow. So find the box that contains potassium on the reactant side. I add 2 more boxes of potassium hydroxide. This now gives me a total of 3 potassium atoms on the reactant side. But these boxes not only contain potassium atoms, they also contain hydroxide ions. And so I need to readjust my inventory list to account for this additional hydroxide. And so now, as I count up the hydroxides, I now have a total of 3 hydroxides on the reactant side. All right. I'm going to skip over hydroxide for just a moment and balance the cobalt. I have 3 cobalt atoms on the reactant side, only 1 on the product side. I need to get 2 more cobalts on the product side. I find the box on the product side that contains cobalt atoms, and that's a cobalt 2 hydroxide box. And so if I add 2 more boxes of cobalt 2 hydroxide, I will have a total of 3 cobalt atoms on the product side. So the cobalts are balanced. But this box not only contained cobalt atoms, it also contained hydroxide ions. So with the addition of the 2 boxes of cobalt hydroxide, I added an additional 4 hydroxide ions to the product side. So I'm going to adjust my list to account for this extra hydroxide. So now I have a total of 6 hydroxide ions on the product side. Next comes phosphate. I have 2 phosphate ions on the reactant side, only 1 on the product side. I need to get 1 more PO4 ion on the product side, and so I find the box that contains PO4. That's potassium phosphate. And if I add 1 more box of K3PO4, I will have a total of 2 phosphate ions on the product side. And now my phosphate ions are balanced. But this box of potassium phosphate not only contained phosphate ions, it also contained potassium ions. So I'm going to adjust my list to account for the 3 extra potassiums that were added to the product side. I now have a total of 6 potassium atoms on the product side. So going back to the top of my list and balancing the potassiums, I need to get 3 more potassiums on the reactant side. So I'm going to add 3 more boxes of potassium hydroxide. And now I have a total of 6 potassium atoms on the reactant side. But when I added these extra boxes of potassium hydroxide, I also added extra hydroxide ions. And so if I readjust my list, I now have a total of 6 hydroxide ions on the reactant side. You will notice this now balances our hydroxide ions. This also completes our work because all of the atoms and ions are balanced from the left to the right side of the reaction arrow. So to get my coefficients, I'm going to add up the boxes. I have 6 boxes of potassium hydroxide, 1 box of cobalt 2 phosphate, 2 boxes of potassium phosphate, and 3 boxes of cobalt 2 hydroxide. Finish up and write my balanced chemical equation. I'm going to leave off the boxes and coefficients of 1, and so I get 6 potassium hydroxide compounds reacts with 1 cobalt 2 phosphate compound to yield 2 potassium phosphate compounds and 3 cobalt 2 hydroxide compounds. So to review the 3 tips or suggestions or shortcuts illustrated in tonight's lesson. Tip number 1, balance atoms that are found in more than one reactant or product last. Our second tip of the night, when in doubt, whip a 2 out, double up one of your reactants and rebalance your inventory list. You might find out that life is a little bit easier. And then our third tip suggestion of the night is when polyatomic ions are not broken up throughout the course of the reaction, then in your inventory list, instead of balancing individual atoms, balance polyatomic ions. If you have any questions, comments about tonight's lesson, please send me an email or a tweet. My contact information is shown. Have a great day and happy studying.